Hello, everyone, and welcome to our webinar. Our topic today is titled Frame for Success, Avoid Callbacks. My name is Mary Ewer, and I will serve as the moderator for this session. Our speaker, Stephanie Thomas-Reese, and I both work for APA, the Engineered Wood Association. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood products and systems where they are used. We also educate users and specifiers on the product's intended use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. Stephanie's presentation will last about 50 minutes. A handout showing the slides can be found in your GoToWebinar dashboard on your screen. To ensure that everyone can hear clearly, we have muted all participants. We encourage you to submit questions by typing them into the questions pane on the control panel, and I will be monitoring those throughout the session. We should have time to answer most of our questions, but if we run short, we'll be sure to post a Q&A summary on our apawood.org website, along with a recorded version of today's program in a few weeks. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized certificates of completion. Our presenter today is Stephanie Thomas-Reese. She is APA's Florida representative. Stephanie is an experienced designer and energy professional with a bachelor's degree in architectural design from Clemson University and a master's degree in energy efficient building from Oxford Brookes University. Her past roles include project architect, energy efficiency director, code compliance coordinator, and adjunct professor teaching high performance strategies, sustainable design, and building materials. With APA, Stephanie consults with designers, builders, and code officials on the proper use and specification of engineered wood products. For those of you just joining us, welcome to APA's webinar, Frame for Success, Avoid Callbacks. I will now turn the microphone over to our speaker, Stephanie Thomas-Reese.
Thank you, Mary, and to everyone participating in this webinar. Let's get started. So this slide outlines what this course is about. We will discuss the material properties of wood. We'll look at being consistent in design and installation of engineered wood products. We're going to recognize the effects of wood products exposed to moisture. We'll understand the importance of complete load path and identify the impacts of wind and seismic forces on structures. To better understand the challenges and opportunities with engineered wood, we need to understand a few basic concepts. So there's 5 main ideas that will help to design and frame successfully. Almost every error comes back to one of these 5 ideas that commonly lead to a misuse or misinstallation of wood. So first, we'll look at some of the basic properties of wood, and we'll start with the fact that wood has a strong and weak direction and has different strength properties in those directions. I like to best demonstrate this when wood is strongest by using a group of straws representing the grains of wood. When a load is applied along the grain, the material is said to be in compression. In this case, the wood is strong. Similarly, applying tension also develops considerable tensile strength in wood. But wood is not as strong when a wood is applied perpendicular to the grain, as illustrated with the straws again. Here, the fibers in the wood can be more easily crushed under load because of the not as strong orientation of the cellular walls. The same applies to a load that seeks to pull the straws apart, as illustrated here by a load applied perpendicular to the grain. Tension perpendicular to the grain can lead to failures in connections or the wood member itself. So when structural plywood is manufactured, the veneers or plies are arranged so that the direction of the grain in each layer is alternated between the adjacent layers. The grain direction in the face and back plies of a plywood panel always create the strong direction of the panel, typically the long dimension. The cross-laminating process of the inner veneers makes the panel more dimensionally stable or flat and also provides greater resistance to splitting. As in the manufacturing of plywood, the strands in each layer of OSB, or oriented strand board, are also cross-laminated, creating a structural direction for OSB, as well as increased stiffness. That strong axis is typically the long direction, unless otherwise noted on the panel. And as with plywood, the thicker the panels, the less movement can be expected with changes in moisture content. So panels will have a trademark stamp on them, and this is what one with the APA trademark looks like. The span rating indicated on the trademark is highlighted here with the red arrow. This notes the maximum distance the panel can span between framing supports. The first number refers to the maximum distance between roof framing members, in this case 32 or 32 inches maximum between the roof framing supports. The second number, 16 or 16 inches, refers to the maximum spacing between floor joists. Now, these two conditions are noted here with the span rating. So first, the structural axis is usually the long direction of the sheathing panels, runs perpendicular to the framing members. And secondly, the panels need to span a minimum of 3 framing members. So this is an area where errors are common. So the panel's not perpendicular to framing, or the panel spanning a single span. When this happens, additional support may be required. So in this picture, we're looking up at the roof decking from inside the attic area. Note the sheathing panels installed on each side of the roof's ridge. There are a couple areas you should note concern with. First, the sheathing on the left of the ridge is oriented in the weak direction between the supports. You can see this by looking at the grain that is running parallel and not perpendicular to the support. If this occurs, blocking should be added to the unsupported edges. Second, the panels on each side of the ridge may be too narrow. The roof sheathing width less than 24 inches in width needs to have one or both edges supported, depending on how narrow they are. So panels 24 inches or wider should be used wherever possible. However, there may be instances where panels are less than 24 inches in width, such as in roof ridges or valleys. In these situations, APA recommends additional edge support. For panels between 16 and 24 inches wide, we recommend the use of 2H clips or 2x blocking at the lower edge. For panels 12 to 16 in width, it's recommended to support the lower edge. And a situation where panels are less than 12 inches in width, they must be supported with blocking at both the upper and lower edges. So I'll pause here and mention that you may see references throughout this presentation to APA publications with form numbers. You can find more information about the topic being discussed in the publication referenced on our website at apawood.org. So for instance, for more information about narrow width roof sheathing, refer to the APA document titled Panel Edge Support for Narrow Width Roof Sheathing. So let's look at I-joists now and how they are constructed. One of the most common products now being used in approximately 50% of residential construction, replacing standard dimension lumber, is the I-joist. They're engineered to take advantage of wood's properties and material to gain the maximum benefit. And the I-joist is commonly used for floor and roof framing, and it has the advantage of long lengths that are light to handle and easy to install. So the first elements consist of the flanges, which can be dimension sawn lumber or structural composite lumber, most commonly LVL. The second element is a web, which is typically made of OSB. This configuration uses the high strength properties of the LVL, or the sawn lumber, to resist deflection and bending moment stresses, and the high shear capacity of OSB in the web to resist the shear stresses in the member. So let's review a little Engineering 101 here. The bending forces on I-joist are caused by various gravity loads. A uniform load most commonly applied to an I-joist is indicated by the red arrows. These forces are carried by the flanges along the top and bottom edges of the joist. In this simple or single span condition, when the beam is loaded on top, the joist bends downward and the top flange is in compression and the bottom flange is in tension. The bending force is greatest at midspan of the joist. So the load also induces shear forces in the joist shown by the green arrows, and shear is transferred through the web and is greatest near the ends of the joist where they're supported. So let's look at it another way, like using my straw. I like demonstrating this with tangible things. If we use this foam insulation like a wood beam, putting a wood beam in bending puts opposite sides, the top and the bottom of the beam, in tension and compression. We said earlier, using the straw, that these were the two strong directions in wood. The bottom portion of the beam is in tension, where those vertical lines spread apart at the bottom edges, and the upper portion is in compression, where the vertical lines are closer together, or compressing. So all this is important for understanding the effects of field drilling holes in I-joists or other beams. Near the bearing point, the shear forces are greatest, so the web material may need to utilize the full design shear value of the joist. Generally, holes in the web material can be larger the further they are from the I-joist bearing. There's additional guidance in the APA publication titled Performance Rated I-Joist Design and Construction Guide, or you can refer to the I-joist manufacturer's literature. Never cut or notch the flanges, and it is recommended that an 1/8" section of web be left at the top and bottom of any opening. So to determine the hole size allowed, and keeping in mind that the shear is greatest near the I-joist bearings, if we draw a line from the top center of the web to the bottom of the web, just above the support, we will have drawn a line that represents the inverse of the shear force. The height of the dotted line at any point approximates the permitted hole size at that location, as indicated by the dark brown holes on the left side. Once that hole size is determined by fitting under this line, the hole should be cut in the middle of the depth of the web, like indicated by the white holes on the right side. When cutting multiple holes, there are some limitations, and as long as the sum of the holes when grouped are no larger than the permitted hole size with respect to its location, and rectangular holes no more than 75% of the allowable sized round hole at that location. Again, more information can be found in our publication. Knockouts are pre-scored holes that some I-joist manufacturers will provide in the joist webs for the pass-through of plumbing or electrical systems. And knockouts do not count as holes and do not have to be included when calculating the end distance requirement. Also, it doesn't matter if these knockouts are at the top or at the bottom of the I-joist when they're installed. So let's look at this example and where the holes are located. They appear too close to the bearing for that size of a hole. Also, multiple same size holes appear too close to each other. And if we applied the hole grouping approach, the hole size would be the total of both holes plus the distance between these holes, which most certainly would violate the hole tables. And never touch the flanges. I-joist flanges are never to be cut, notched, or in any way modified, even by the plumber here. Also, this fire caulking is not an acceptable structural repair. LVL. So laminated veneer lumber is comprised of veneers or plies of wood laminated together to create beams or columns similar to plywood. The veneers are oriented in a parallel direction to provide the maximum strength in bending. LVL is a type of structural composite lumber which is available in longer lengths than conventional lumber. Cutting of holes in an LVL is pretty straightforward. Holes can only be cut through the middle third of the height of the beam and the middle third of the length of the beam. And by cutting in this area, we are locating holes away from the support where we learn that the shear is greatest and away from the beam edges to minimize the impact on the allowable moment of the beam. And the maximum hole size is 2 inches and as always, Check with the manufacturer's recommendations, as our technical notes only provide general recommendations. Field modifications to LVL beams are possible, but this is an example where the creative plumbing and wiring seem to fall outside of common sense. None of the holes through the beam members or the notching of the underside of the beam members fall into those allowables for the drilling and notching guidelines. And look at this notched LVL. In this case, a shorter, oops, I went too far, sorry. A shorter cripple stud would have been better suited here. But the diagram to the right demonstrates the rule of thumb for LVL notching. The tension side should not be notched more than 10% the depth. So that business card that you see wedged into the notch is about 2 inches. And unless this LVL is greater than 20 inches deep, the notch is outside of our recommendations. That inset photo you see at the upper right also shows how the straws or the wood fibers want to separate when the bottom of that beam is notched. Laminated strand lumber, another type of structural composite lumber, and that incorporates wood strands as opposed to veneers and adhesives to create a structural beam or vertical framing members, columns, or studs. Another good engineered wood product is glue laminated beams, which are manufactured by typically gluing nominal 2x lumber of varying widths from 2.5 inches to 10 3/4 inches into single beams. Like LVLs, the wood grain runs parallel to the length of the beam, which takes advantage of wood strength properties. As engineered wood floors became more popular, it was important for all beam manufacturers to be able to offer products that are compatible with common I-joist depths for the ease of framing and finish. I-joist compatible or IJC glulam beams are readily available and used in all markets. When the laminations are being laid up into a beam, attention is given to the location of the natural strength-reducing characteristics found in lumber, such as knots and knot holes that you see. Sometimes you'll notice that the laminations can be finger jointed, which allow manufacturers to make beams of almost unlimited length. Now, we talked about this in I-joist, but just to reiterate again, in glulams, that when simply supported at each end, the shear force is 0 in the center and reaches its maximum at the supports. And conversely, the bending moment is 0 at the supports and reaches its maximum at the center of the member. The stretch from bending is the highest at the top and bottom laminations of a glulam beam throughout the center of it lengthwise. Understanding these concepts is important to recognize balanced and unbalanced beams. A beam manufacturer can take into account the tension and compression sides in the beam design. When manufacturing an unbalanced beam, there's different grade laminations in the top and bottom of the beam, and it allows for more efficient and economical design in simple span situations. In a multi-span or cantilevered application, the beam is balanced and can accommodate both sides being in tension. When an unbalanced glulam or cambered beam is being installed, there is a top and a bottom. The word top will be clearly stamped on the top surface of the beam. Installing the beam right side up assures that the high strength tension laminations are located on the bottom of the beam. So, if you notice this situation while in the field and you look up and see this, the glulam has been installed upside down and likely won't have the strength expected by the designer. APA has guidance on the strength of upside down glulams, and we tend to joke about this. If you see it installed like this, TOP also means turn over please. Now, similar to I-joist, the highest strength wood fibers are placed in locations where they're most needed in a glulam beam. And because of this, it's important to ensure that holes are located appropriately and the compression and tension zones should not be modified without engineering analysis. APA's publication, Field Notching and Drilling of Glue Laminated Timber Beams, provides diagrams like this one, shown here, on how many holes are allowed, size limitations for horizontal and vertical holes. It also provides guidance on field notching glulams. So that takes us through the strength direction of wood. And we talked about panel installation, holes and notches and beams and other important concepts. The second consideration with designing and using engineered wood is that wood changes in dimension as it changes in moisture content. Just as steel, plastics, and glass shrink and expand with changes in temperature, wood moves with changes in its moisture. So APA recommends that plywood and OSB sheathing, siding, and other products be spaced 1/8 of an inch from adjacent panels when being installed. The reason for this is that structural panels are manufactured at a relatively low moisture content. They are manufactured dry. It may not be until they reach the job site and are installed that they are exposed to weather or humidity. The recommended 1/8 inch spacing at all panel ends and edges allows for this expansion to take place as the moisture content of the panels elevates and the panels expand in both width and length, and to some extent in thickness. In a worst case scenario, it doesn't take much for the panels to buckle out of plane in width or length. So this diagram shows that in the long direction, if not supported, you could have over 2 inches of buckling upwards after expansion. In the shorter 4-foot direction of the panel, it could buckle as much as 1.5 inches. And the 1/8 inch gap helps mitigate this. Here we see OSB panels being used as wall sheathing, and that box cutter stuck in between the panels indicates that the framer did not leave an 1/8 inch space between them, and they expanded with increased moisture content. So you can see buckling outward and inward between the wall framing. And after the wall is finished, it could look like this, which homeowners are not particularly fond of. So while this is not a life safety issue, it is an aesthetic one that can be avoided with ensuring the gap during installation of the panels at all edges. As with wall sheathing, it's important to space roof sheathing panels to 1/8 of an inch at both the long edges and butt ends of the panels. And even though most spacer-type panel clips help space the roof sheathing, those clips are only used along the long edges of the panels. The butt ends of the panels are always supported by the roof framing, and these panel ends need to be spaced as well. Or this is the potential outcome of failure to adequately gap roof sheathing panels. As you can see, the butt ends of the panels are tight together. It is likely that the same was true at the time of installation, which would restrict the panels from expanding in length when they took on moisture. Some applications of wood structural panels can lead to a higher risk of wall buckling. APA's technical note provides recommendations to reduce the potential of buckling when using wood structural panels. It highlights some high-risk conditions, like when long dimension of panels are parallel to the supports, when engineering calls for tighter nailing pattern, which can reduce the gap's effectiveness and restrains the panel from expanding, and when long construction schedules with extended exposures to moisture impact the panel expansion. So here's a case where the gap was provided, but the tight nailing pattern restricted movement and forced the buckling. So we have two side-by-side photos of the same wall. On the left, you can see that the panels were severely buckled using a straight edge. And on the right, you'll notice that there was a gap and still is one. So why did they buckle? So if we look at the nailing pattern, the panels were fastened 2 to 3 inches on center. Nailing that's this tight can prevent the panels from expanding into the gap provided. Such overly restrained panels are prone to buckling. And one way to avoid this is either let the panels acclimate prior to installation or fasten them initially with a less intensive nailing pattern and then come back later to do the tighter shear nailing. Now, this may be an issue in high wind and seismic prone areas. Panels aren't the only wood that moves with changes in moisture content. Here you see an image of a glulam in a beam hanger. Wood beams will typically shrink after installation because of their moisture content drops, which is the opposite of panels, which are manufactured at a lower moisture content. If the bolts are at the top, it can cause the beam to not sit in the hanger as it shrinks, and this will induce stresses at the bolt locations. It may eventually split and result in the beam sitting in the hanger seat. And so here's an example pictured of that exact thing happening. If you look closely at the bottom arrow, you can see that a business card was easily slid between the beam and the bearing location at the bottom of the beam. This beam is experiencing stresses at the bolts that it was not designed to handle, that the top two arrows are pointing to. Wood laminations in Glulam are limited to about 16% moisture content or less, which results in fewer seasoning checks than sawn lumber. These checks are noted by the presence of torn fibers and should not be confused with an adhesive failure or a delamination, even though they occur near a glue line. Seasoning checks are seldom a structural concern, but they do impact the aesthetics of the beam. To minimize checking, install glulam in environments with consistent humidity levels and control the moisture content of the beams by protecting the wood from high moisture areas such as concrete or refrigeration, and thoroughly seal the beams on all 6 surfaces. Now, end checks originate and generally stay in the location of the end of the member. If an end check has a length of less than half the depth of the member, there's no concern. It is important to recognize the difference between a check and a split. A split is a separation the full width of the member. The second type is a side check, where the opening is parallel along the side face of the member. If the side check is no greater than 1/3 the width and 1/3 the length, there should be no concern. And the third type is a bottom check. That occurs on the bottom face of the member. And as long as the check remains parallel to the grain, these can be of any length and not pose a structural concern, even if full length. If the checking in beams becomes a concern, you can refer to Owner's Guide to Understanding Checks in Glue Laminated Timber, which details a flow chart to evaluate checks in beams. All right, so we've talked about the strength direction of wood as well as the fact that wood moves with changes in moisture content. Let's discuss why consistency is key. Consistency in framing alignment is critical in providing flat surfaces of floors, walls, and roofs. If rafters or trusses are not consistently cut or they are out of alignment, the surface of the roof will be uneven, as seen here looking along the ridge of this roof. The roof sheathing will not lay more flat than the framing member it's attached to. While from the ground, it may appear as though the roof sheathing is the cause of unevenness in the finished roof, it may actually be the alignment of the framing that's the problem. So a low sun shining across the roof really exposes those roof imperfections. Ugly roofs are often due to the failure to properly install the roof framing, the roof sheathing, or both. In this case, panel edge swell was suspected as the problem. However, the high truss in the middle of the roof can easily be seen where 2 pieces of plywood meet on this truss. The ends of the panels can ridge up and raise the shingles. If you look carefully, the high truss is still visible where the plywood spans across at the red arrow. It's just not as noticeable as where the panels end on the truss. To help minimize roof imperfections, make sure the framing is consistent and the roof sheathing is installed per APA recommendations. Pay attention to proper ventilation rates, as well as when other trades access the attic, the vents could get covered up by insulation. And one last thing that can help mask roof imperfections is the use of heavier, laminated, or dimensional shingles. Another place where it's important to be consistent is the type of floor framing materials used. I-joists should never be mixed with lumber framing, as seen in this floor system where a lumber band joist was used. An engineered wood I-joist will be slightly taller than the dimension lumber, as seen at the arrow. Always use an engineered wood rim joist like OSB rim board, LVL, or another structural composite lumber product with an I-joist floor system for compatibility. Generally, I-joists are manufactured to different depths. In this case, the I-joist is 11 7/8 inches, and the 2x12 is 11 1/4 inches. I-joists are also manufactured to tight tolerances, and those tolerances and the fact that they are manufactured dry makes them a perfect match for use with similarly dry OSB and plywood floor sheathing. When dry floor sheathing is properly attached to dry engineered wood I-joists, squeaks and other floor noises are minimized. The floor squeaks are caused by differential movement in the floors. To avoid this, floor sheathing should be both nailed and glued to the panels. In fact, most fan tables for I-joists are based on a glue floor system to make sure that the panels and the joists work together. APA also recommends glue in the groove side of the tongue and groove subfloor panels, which can be another source of unwanted floor noise. So the proper method is to install glue nailed floor system is to make sure the I-joist or the framing member is free of dirt or debris. Spread just a small bead of glue, about 1/4 inch, from one side of the panel to the other, and don't have any glue gaps or mounds that will spill over. Glue the groove. We want to lay it in fresh adhesive, making sure the glue doesn't dry before you get the panel laid down. And fasten, applying foot pressure at each and every framing member under the panel, which means stuffing on the member while fastening. This was not as problematic back when we used hammers because the hammer was more likely to drive both the nail and the panel down tight. Pneumatic nailers, however, can drive the nails without pulling the subfloor panel tight. So make sure you're stuffing on the panel at the support. Of course, the more nails that miss the framing, the greater the chance of floor problems. These missed nails or shiners increase the likelihood that there will be movement between floor components and cause squeaks. In this picture, where the arrows are, we see the inconsistent joist spacing that can make a homeowner feel uncomfortable when they're walking across it. The different spans will cause a change in floor stiffness and may even exceed the code or the span ratings. The floor framing areas that are framed dramatically different can result in those floors feeling different. So in this example, there's several areas of the floor which may feel different. So we have an area with a short joist span adjacent to an area with long joist span, and then next to that, an area with the wider joist spacing, and an area where the direction of the floor joist changed altogether. So these differences greatly affect how the floor feels to that homeowner, creating customer dissatisfaction. It may be worth reevaluating the framing and consider spacing joists more uniformly, resulting in a more satisfied homeowner. So this layout not only provides more consistent performance, it can eliminate the joist layout direction change and change in panel orientation, making it easier for the framer. So far, we've covered strength of wood, wood movement, changes in moisture content, and the importance of consistency. The fourth concept we'll discuss here is perhaps most important to durable construction. Understanding load path, or how forces travel through the structure of the building and into the ground, is vitally important. All loads must find their way to the foundation and into the ground. Code requires complete load path capable transferring loads from their point of origin to the load resisting elements. And we have vertical load and lateral load paths that must be addressed when designing for load path continuity. Vertical load paths are pretty easy to understand and basic. It starts with us as infants when we're learning to walk or tossing a ball. What goes up comes down. Gravity works 24/7 and is very consistent. And following the path from the ridge of the roof to the foundation is pretty straightforward. The load path is simply the path that the load takes as it passes through the structure and its components and connections on its way to the ground. In the vertical load path, members above bear on members below, thereby transferring those loads from above all the way to the foundation. In designing vertical load paths, continuity is important. Removing a section of material interrupts that load path, resulting in other members needing to support these loads, and they may not be up to the task. So in this example, the joist has been cut for the plumbing. This can overload the OSB sheathing by doubling the span of the sheathing along the length of the cut joist. It would likely require some header joist at the cut ends to provide additional support for the cut joist and properly transfer load to the adjoining members. This notch is not okay either. It can impact load paths. Notches are never permitted in the top or bottom flange of an I-joist. Horizontal floors and roofs collect the loads and disperse them to the walls. So those loads move from joist to wall studs and rim boards or beams. Where the joists don't or cannot bear directly on the other members, lightweight metal connectors, such as joist hangers like the ones pictured here, can be used. When using a joist hanger and other connector, make sure each hole in the connector has a fastener and the correct fastener is used. Also make sure the hanger is approved for the specific I-joist size and loads being transferred. In the picture to the right, the joist hanger is wider than the I-joist, and because it is not tight against the flange, it's rotated and could cause floor squeaks and an uneven floor. The dimension lumber and I-joist are different in several ways. While I-joists can span longer distances, thereby providing more design flexibility, they also have a reduced cross-section at the web that requires special consideration for concentrated loads. Therefore, heavier vertical loads need to be carried around the I-joist instead of through the I-joist. As this diagram suggests, overloading the joist can cause the web material to bow out of plane or cause the web to actually knife through the flange material. We can prevent this by using squash blocks to carry the load around the joist. Squash blocks are cut just slightly longer than the height of the joist so that they will carry the load around the joist. They're often cut from dimension lumber or pieces of rim board that match the joist height and are the width of the supporting wall or beam. In this photo, it appears as though a large point load from above was too great for this I-joist, causing it to buckle. Squash blocks on either side of this joist could have allowed the point load to be safely transferred to the wall below. Other ways to transfer loads around I-joists is to use the APA rim board, structural composite lumber, or an I-joist. In this instance, the rim board, in addition to providing lateral support for the I-joist ends, also transfers the vertical load from the bearing wall above. Now keep in mind the minimum required bearing length for an I-joist at the end is 1 3/4 inches. And here's another option for transferring load using blocking panels. These details and others are available in APA's performance-rated I-joist design and construction guide that also provides load capacities for the designer to utilize and prescribe scenarios like these. There's many occasions in which the structural and/or architectural layouts specify the use of multiply engineered wood flush beams. It's important to follow the connection details of the project engineer or those of the manufacturer in order to safely connect these members so that they may act as a unit to transfer loads. This is important in load path continuity. As you can see in this photo, a flush beam has been created by using 2 LVL members that have been connected with bolts. And this connection is important so both plies can carry an equal share of the loading forces. Now, while the vertical load paths are pretty straightforward, another type of load path, lateral load path, is not as intuitive. With the frequency of turbulent weather events in all parts of North America, there's a greater awareness of the importance of designing to resist strong wind loads. So this schematic shows how the lateral or horizontal load path transfers the forces to the ground. If the forces don't reach the foundation, there will be a failure. In a simple building, the forces begin at the wall in one direction and then transfer into the roof via the connections. The roof then transfers the force to the walls at each end of the structure. And these walls, see at number 5, become the shear walls and carry the load into the foundation, completing the load path. Another way to envision the lateral load path is thinking back to the vertical load, but acting sideways on the house. So think of the house as being tipped on its side, and you can see that the lateral loads need to travel to the foundation just like the more familiar gravity load. This just shows that the gravity connections alone aren't going to resist the lateral loads. There are three types of failures that are commonly seen from lateral loads: racking, base shear, and overturning. And we'll look at each of these and how to resist those forces. So narrow walls at garage doors is a common place for failures. This home had inadequate wall bracing or shear walls in this area and racked due to the high wind loads. This was caused by an estimated EF2 tornado in Texas, and you can see that there are two primary failure points in this narrow wall: at the base of the wall segment and at the hinge at the top of the segment. A continuously sheathed portal frame is one of many options the IRC depicts to help resist racking at narrow walls. We could spend an hour alone on this. One option in the IRC that doesn't require hold-down devices, but relies on a continuously sheathed wall line, nails, anchor bolts, and an extended garage door header can be used. And APA has very detailed guidance and multiple tools on this topic, including a dedicated webinar available on our website. Another lateral force, base shear, is caused by a lack of anchor bolts into the foundation. So here you can see the CMU foundation wall with no anchor bolts, which means that while the home is strong enough to resist racking, it slid off of its foundation. And overturning failures are less obvious in the field. When we see overturning failures, they often look more like a pile of rubble because the other connections failed as it flips over. But we do see them in sheds and smaller buildings like this doghouse often. The overturning failures are caused by insufficient hold downs into the foundation. Here, while under construction, you can see that the hold downs were installed. However, the spalling concrete at the circle means that the hold down won't work as intended. This is another area where it's important to pay attention and avoid potential failures due to wind loads. Here you see a two-story wall was framed with a hinge. With two-story platform framed houses, the hinge between the stories is a weak point. One way to eliminate these hinge locations is with the use of engineered wood full-height studs. Tall structural wall systems can be framed with engineered wood framing that add both strength for the wall and ease of construction for the builder. Here, the builder used glulam columns that extend the full height of the room, ensuring that the load from above can continue uninterrupted. Now, this is a publication we have that provides above-code methods to improve the performance of homes in high wind events. It shows examples of failures that we've observed following storms over the past 15 years and provides a good step-by-step connection details to tie together exterior walls, roofs, and floors, ensuring load path continuity. So we've covered those first four main ideas. Our last concept that we're going to discuss is protecting wood frame systems from moisture. Moisture impacts all construction systems, steel, masonry, and concrete, as well as wood. The best way to prevent moisture intrusion is to use gravity to manage rainfall. The first priority is to deflect rainfall to prevent it from hitting the wall. The rain that does hit the wall can be allowed to drain away using exterior cladding and a secondary water resistive barrier under the cladding. If and when water does penetrate the primary and secondary water barriers, the wood assembly must have a means to dry. And finally, using durable building materials in locations that are exposed to longer-term wetting, such as where wood is in contact with concrete. So in this picture, the gutter is removing the water from the roof, but directing it toward the wood siding instead of away from the building. and the mold on the siding is an early indicator of problems to come. Plus, there should be a minimum 6-inch clearance of the siding to grade. Now, it's taken a lot of education, but we're seeing fewer instances like this where the water-resistive barrier is only installed at the conditioned space locations. In this case, the house wrap should be installed over all the exterior wall sheathing, including both the gable end and the lower portion of the wall. Again, deflection is the first line of defense. It's generally not a good design idea to have water from the roof dumped into the edge of a window. This can create drainage into the wall system. The use of a kick-out flashing is always a good consideration at the wall and roof intersections to deflect water away from the home. Also, there's no clearance between the siding and the shingles at those red arrows, potentially allowing moisture to migrate up into the wall system. So this is a good example using kick-out flashing to divert roof runoff away from the wall and into a gutter. Treated beams and columns for exterior use are important for the life of the structure. This deck makes use of preservative-treated glulam beams. Prolonged high moisture contents can lead to wood decay. Therefore, preservative-treated or decay-resistant species wood should be used in cases like this. So attic ventilation is critical, not just to keep your attic area cooler in the warmer months, but to allow fresh air into and out of the attic space, circulating the air, minimizing the buildup of moisture, and minimizing the condensation of the moisture on cold surfaces. Now, clogged baffles can lead to elevated moisture levels by compromising those ventilation strategies. Here, you can see in the picture to the left, the shingles raised due to panel expansion because of a bathroom exhaust pipe that did not get vented properly through a roof or soffit. Poor exhaust strategies in the attic area, like this, can lead to mold growth as well as increased movement in the roof sheathing. As the panels expand beyond the space provided during installation of the sheathing, it caused the shingles to raise at that expansion. Now, the image to the left is a multi-floor project that experienced delayed dried-in time and has standing water on it. It would help drying to drill holes in the subfloor and allow the water to drain. A critical issue while these floors are drying, especially a multifamily project, is to make sure the panels aren't damaged while wet, like from heavily loaded drywall carts and loaded ladders. Now, the image on the right shows where the vapor barrier in a basement wasn't installed properly, which could lead to elevated moisture levels in the crawl space. This can be accomplished through the use of fans or dehumidifiers. And contrary to popular belief, many temporary heating systems, including propane, actually introduce moisture to the air instead of removing it. Additionally, the National Wood Flooring Association recommends, if possible, that heating and air conditioning systems be operating prior to the installation of hardwood flooring. Now, referring again to the APA trademark panels, may be produced in two bond classifications. You'll see this at the location on the trademark where that red arrow is, exterior or exposure 1. This bond classification relates to the moisture resistance of the glue bond. So if you want to have panels that will resist all of the moisture and long-term weather exposure, use exterior. Exterior panels and bonds capable of withstanding repeated wetting and redrying. Exposure 1 panels are suitable for uses not involving long-term exposure to weather, but are intended to resist the effects of moisture due to construction delays or similar conditions. And in any event, this is not a good example of properly storing wood products to prevent excessive moisture. We want to make sure that we keep those unused products covered. So that takes us through all 5 main ideas. We discussed the physiology of wood and how it impacts how you design and install wood products. We talked about wood as a material that has the ability to absorb and exude moisture. And this wetting, drying allows wood to move. It shrinks while drying or grows when wetted. And recognizing this, we can design and install details that accommodate this movement. We should strive for consistency, balance the floor system, use the correct materials, and make sure framing is aligned. We discussed that all loads, vertical and lateral, must make it to the foundation. And last, dry wood is good wood. This is the best advice I can give with wood construction. Keep it dry. If it gets wet, let it dry, and protect from moisture, remembering the 4 Ds: deflection, drainage, drying, and the use of durable materials. And with that, I thank you for your time, attention, and I'll turn it back to Mary if any questions have come through.
Hey, we have had some questions, Stephanie. Thank you for all of the really, really good information. We've had a number of questions come in, so we'll get through what we can here. The first one that came in is, throughout your presentation, you referenced nails a number of times. Can staples be used instead?
Yes, staples can be used instead of nails. The IBC and the IRC specify requirements for sheathing fasteners, including staples. There's a table that specifies fasteners, and for staples, it permits wire staples with a minimum 7/16" diameter crown. The other specifications on staples and other power-driven fasteners, you can contact the International Staple, Nail, and Tool Association, or ISANTA, because they have tables that recognize power-driven fasteners, including staples and nails. And one last thing on using staples, we want to make sure that they're installed with the crown parallel to the support below. This helps to make sure that both legs of the staple get good embedment into the support.
That makes sense. So in a wall application, you would want to run the crown of the staple vertically. Is that correct?
Correct.
Okay, that makes sense.
It's parallel to the support.
The stud. Another question just came in. Well, a lot of them came in. I have them all popping up on my screen here. How do you define long-term exposure for exposure 1 panels?
So there's really no quantitative number to say because it depends on the climate, depends on the situation, the season, the climate, the location, literally. So for instance, we can't say 5 inches of rain because 5 inches of rain in Arizona is a lot different than 5 inches of rain in Florida. We can't really use a time frame, say 2 months of exposure, because 2 months exposure in January in Washington State is different than 2 months exposure in July in Southern California. So again, what's important is to keep it as dry as possible, keep it covered, keep it protected. If it gets wet, allow it to dry. And again, just make sure that it's not damaged by heavy point loads or anything while it's being allowed to dry.
Thank you. That's helpful. It makes a lot of sense that, you know, even for you and I, you're in Florida and I'm in Baltimore, and we have very different climates. Can you talk a little bit more about why we can't mix a sawn lumber rim joist with engineered wood I-joists?
A few reasons, and I think I touched on those in the slides, but first reason, they're manufactured to different depths. So like I said earlier, the 2x10 dimension lumber is actually 9 1/4 inches deep, and 2x12 11 1/4 inches deep. And I-joists, the depth of those respective I-joists are 9 1/2 and 11 7/8. That means when you use a sawn lumber rim joist with an I-joist, it would be lower than the I-joist, which leads to a change in that load path from what was intended. And the I-joist webs are typically manufactured with a 3/8 inch OSB, and although they're rated to resist gravity loads, they don't have the same strength. Also, when mixing the sawn lumber with structural composite lumber, we need to remember that they have different drying capacities. The sawn or dimension lumber is likely to shrink, and the composite lumber, which is manufactured in dry conditions, is likely to grow. So that differential movement can also cause inconsistent load path or unevenness in the structure or other concerns. And again, we have some additional technical notes titled Wood I-Joist and APA Performance Rated Rim Board that explains this even more.
Thank you. This is one that I would guess a number of our attendees can relate to. What do I do if my plumber or electrical contractor punched a large hole in an I-joist? How do I know if it's okay, and where do I find repair details?
Again, I did reference the APA's Performance Rated I-Joist Design and Construction Guide publication. It provides some general guidance for holes, as long as all the slides that I showed earlier, but just remembering the flanges should never be drilled, cut, or notched. And if that's not enough information, definitely refer to the manufacturer's published information for additional information or guidance. And I-joist repair can become a complicated engineering problem. So if the manufacturer should be able to help you solve it, as well as the engineer of record.
Thank you. We've had a couple of questions on buckling and tighter nailing. As you know, there are areas in the country where tighter nailing is required by the structural codes, and we're aware of that too. So when the panels are tacked up in place, and we recommend that initial tacking to allow them to expand, is there a length of time that they need to sit there before you go in and fill the nails back in? So, you know, the rest of the nails? I'm combining a bunch of questions here. Did that make sense to you?
I think so, and I think it goes back to how long can a panel be exposed. Again, it really depends on where it's located, but we just want to make sure that the panels have a chance to acclimate, and tacking them, say if you're in Florida and we have a tight nailing pattern on the coast and engineers required 3 inches on center as opposed to APA's recommended 6, then we would recommend that you would tack it at 6 and come back later. Defining that later may just mean how much moisture is in the air at the time, and just making sure that those panels have a chance to acclimate and grow, and then come back and finish that shear pattern that's required, the tighter nailing pattern. I hope that answers their question.
I think that answered a couple of questions, and I appreciate your patience as I tried to combine them into one, because we had a number of questions on that. So I think that answered 4 or 5 questions all at once. We have time for a couple more questions here. Is CDX plywood rated for exterior use? Can you use that outside?
So CDX is a bit outdated, and we recommend that term's not used, but you won't find CDX used in plywood grade rules or building codes. That being said, we know it's still used. It's merely slang for what is actually CD exposure 1 plywood, and sometimes it's thought that the X stands for exterior. And realistically, if you order CDX, you will probably get an exposure 1 panel. So exposure 1 panels, as I mentioned before, are suitable for uses not involving long-term exposure to weather, but are intended to resist the effects of moisture due to construction delays or other conditions. So my advice, if you see CDX on a plan, it might be a good idea to talk to the specifier about their intentions, but CDX should not be used for exterior use.
Thank you. Last question. When re-roofing and re-nailing a new roof onto an existing roof deck, do additional fasteners hinder the strength of the decking?
So each situation is unique and should be evaluated by a qualified professional with direct knowledge of the specific condition. But in general, we see no reason to arbitrarily replace roof sheathing panels that undergo roofing replacement. When considering the impact of nail holes, there's little to no reason really to expect appreciable reduction to wood structural panel capacity or performance. The reason being, as the nail penetrates the wood of the nail separates most of the wood fiber instead of boring or breaking through the fiber. So that same may be said of small, minor panel surface damage. A small amount of fiber may be lost, but it may not necessarily be significant when evaluating the entire panel. So again, at some point in the roof's history, there's probably should be some sheathing replaced, but we believe, however, that, again, placing an arbitrary limit on the number of re-roofing is unduly conservative. So the decision on whether to replace the roofing panels should really be determined by qualified professionals such as an experienced contractor, architect, or engineer.
Great. Thank you again, Stephanie. That was really good information. That is all the questions that we have time for today. As I stated before, the questions we did not get to will be posted along with a recorded version of this session on our website in a couple of weeks. Before we conclude, I'd like to touch on 3 other quick things: a short survey, CEUs, and upcoming webinars. We would really appreciate receiving your feedback through the survey that you'll receive in about an hour. So please take a minute and fill that out. Also, don't forget to download your certificate of completion from the link in a follow-up email that you'll receive after the webinar ends. And finally, make sure that you're signed up to receive our APA update newsletter so that you will be notified of our future webinars and updates to APA publications and standards. To receive it, all you need to do, starting from the homepage of our website, is to click on Sign in the upper right-hand corner of the page. In the menu that drops down, simply select Register. From there, you will need to let us know what you'd specifically like to receive, which in this case is the APA update newsletter. I should mention that if you have technical questions on any topic related to the use of engineered wood products, don't hesitate to contact the APA help desk at the address shown here. Stephanie is just one of the field staff we have throughout the country. These talented people are available to assist design professionals, builders, and code officials. Their individual contact information can be found on our APA website, www.apawood.org. Please feel free to reach out and take advantage of this research. As I mentioned, a recording of today's webinar and answers to the questions that were asked will be posted at apawood.org in a week or two. And with that, I'd like to thank you for attending. Have a wonderful day.